Hello, everyone. Today we're gonna focus on 2.1 motion. Mechanics is branch of physics which concerns with forces and how they affect body's motion. Kinematics is a sub-branch of mechanics which studies only the body's motion without regards to causes. And dynamics is sub-branch of mechanics which studies a force which causes body's motion. Kinematics is a study of displacement, velocity, and acceleration, or in short, study of motion. Study of motion begins with a position and change in position. Consider Fred is a fly and his quest for food. The distance Freddy travels is simply how far he has flown without regards to direction. Freddy's distance is 6 meters. Distance is simply how far something has traveled without regards to direction. Freddy has gone 6 meters. Displacement, on the other hand, is not only distance traveled, but also direction. Displacement is 6 meters in the positive x direction to the right. This makes displacement a vector quantity. It has a magnitude and a direction. We say Freddy traveled through the displacement of 6 meters in the positive x direction. Let's revisit some previous examples of a ball moving through some displacement. Displacement A is just 15 meters to the right. Displacement B is just 20 meters to the left. Distance is 15 meters and distance B is 20 meters. There is no regard for direction in distance. So distance is a scalar quantity with magnitude only. Displacement is a vector quantity with direction. Now, for some detailed analysis of these two motion, displacement delta x has a following formula. Final position minus the initial position. Use the displacement formula to find each displacement. Note that the x equals to 0 coordinate has been placed on the number line. For A, displacement equals 2, final position 10, minus initial position minus 5. That gives us plus 15 meters, which is to the right. For B, displacement equals to final position minus 10, minus initial position plus 10. That gives us minus 20 to the left. Velocity is a measure of how fast an object moves through a displacement. Therefore, velocity is a displacement divided by time and is measured in meters per second. So formula is displacement over time. Find the velocity of the second ball if it takes 4 seconds to complete its displacement. For B, displacement is minus 20 meters, but time is 4 seconds. Therefore, velocity equals to displacement over time. Displacement is minus 20 meters, and time is 4 seconds. That gives us minus 5 meters per second. Note that velocity inherits its direction from displacement. From the previous example, we calculated the velocity of the ball to be minus 5 meters per second. Therefore, the ball is moving 5 meters per second to the left. With disregards to direction, we can see that the ball's speed is 5 meters per second. We define speed as distance divided by time with disregard to direction. A runner travels 64.5 meters in the negative x direction in 31.75 seconds. Find her velocity and her speed. Her velocity is displacement over time. Displacement minus 64.5 times 31.75. That gives us minus 2.03 meters per second. Her speed, just the distance over time, distance traveled is 64.5 times 31.75. That gives us 2.03 meters per second. Acceleration is a change in velocity over time. And formula is acceleration equals to final velocity minus initial velocity over time taken. A driver sees his speed is 5 meters per second. He then simultaneously accelerates and starts a stopwatch. At the end of the 10 second, He observed his speed to be 35 meters per second. What is his acceleration? Final velocity, 35 meters per second. Initial velocity, 5 meters per second. And the time taken is 10 seconds. Use acceleration formula. Final velocity minus initial velocity divided by time taken. We substitute and calculate. Final velocity 35 minus initial velocity 5 divided by time taken 10. That gives us 3 meters per second. Why is velocity a vector? Why is acceleration a vector? Velocity is displacement over time. Since the displacement is a vector, so is velocity. Acceleration is change in velocity over time. Since velocity is a vector, so is acceleration. Back in 1950s, military aeronautical engineers thought that human could not withstand much of an acceleration and therefore put little effort into pilot safety belts and ejection seats. An Air Force physician by the name of Colonel Stapp, however, thought human could withstand higher acceleration. He designed a rocket sled to accelerate at up to 40 G, at which acceleration you would feel like you weighed 40 times your normal weight. A human to be tested would be Stapp himself. An accelerometer and a video camera were attached to the sled. Here are the results. Wow, it's pass out, I think. In 1954, America's original rocket man, John Paul Stapp, attained the then world record land speed of 280 meters per second, going from a standstill to a speed faster than 0.45 bullet in 5 seconds on an especially designed rocket sled, and then screeched to the dead stop in 1.4 seconds, sustaining more than 40 Gs of force, all in the interest of safety. There are two accelerations in this problem. The speed up from 0 to 280 meters per second in 5 seconds. He slows down from 280 meters per second to 0 in 1.4 seconds. Find Stapp's acceleration during the speeding up phase. Acceleration, final velocity minus initial velocity divided by time taken. Final velocity is 280 meters per second. Initial velocity is 0 meters per second. Time taken is 5. That gives us 60 meters per second. Find Stapp's acceleration during the slowing down phase. Final velocity stops, so 0 meters per second, and initially 280 meters per second divided by time taken 1.4. That is minus 200 meters per second. Consider a car whose position is changing. A patrol officer is checking its speed with a radar gun, as shown. Radar gun measures the position of the car during each successive snapshot shown in yellow. How can you tell that the car is speeding up? What are you assuming about the radar gun time? We can label each position with an X and time interval between each X with a constant delta T. Then velocity A equals to position 2 minus position 1 divided by time T. Velocity B equals to position 3 minus position 2 divided by delta T. And finally, VC equals to position 4 minus position 3 divided by delta T. Focus on interval from x2 to x3. Note that the speed changed from x2 to x3, and so VB is not really the speed for that whole interval. We say that VB is the average speed. If we increase the sample rate of the radar gun, makes the delta T smaller, the position will get closer together. We call the limit as delta T approaches 0 in the equation, velocity equal to change in displacement over change in time, the instantaneous velocity. By the same reasoning, if delta T gets smaller in the acceleration equation, our acceleration calculation becomes more precise. We call the limit as delta t approaches 0 of the equation a equal to change in velocity, change in time, the instantaneous acceleration. The equation for uniform acceleration motion are also known as kinematic equation. They are listed here, and they are on your data booklets. They can only be used if the acceleration a is constant. They are used so commonly throughout the physics course that we will name them displacement, velocity, timeless, and average displacement. Everyone knows that when you drop an object, it picks up speed when it falls. Galileo did his famous free fall experiment on the Tower of Pisa long ago and determined that all objects fall at the same acceleration in the absence of air resistance. Thus, as the next slide, we will show an apple and a feather will fall side by side. Consider the multi-flash image of the apple and a feather falling in a partial vacuum. If we choose a convenient spot on the apple and mark its position, we get a series of marks like so. Now we scale our data. Given that the apple is 8 centimeters in a horizontal diameter, we can superimpose this scale on our photograph. Then we can estimate the position in centimeter of each image. Suppose we know that the time between image is constant, 0.056 seconds. We make the table starting with the raw data column of t and y. We then make calculation column in delta t, delta y, and velocity. To find delta t, we need to subtract 2 t's. Therefore, the first entry for delta t is blank. Same thing for first delta y. Since velocity equals to change in displacement or change in time, the first v entry also blank. To find delta t, we need to subtract 2 t's by convention, current t minus the previous t. So delta t is constant. To find the delta y, we need to subtract 2 displacements by convention, current y minus previous y. Minus 22 minus 9. Minus 37 minus 22. Minus 55 minus 37. To find a velocity, we need to divide delta y by delta t by convention, current delta y divided by current delta t. Minus 9 divided by 0.056. Minus 13 divided by 0.056. Minus 15 divided by 0.056. Minus 18 divided by 0.056. Now we plot velocity versus t on a graph. The points. Best fit line. The graph velocity versus time is linear and acceleration is constant. Finally, the acceleration is a slope of the velocity versus t graph or gradient of the velocity versus t graph. Run 0.224 second and rise is minus 220 centimeter per second. Acceleration equals to rise over run minus 220 centimeter per second divided by 0.224 second. That gives us minus 982 or minus 9.82 meter per second per second. Generally, we have 4 formula on our data booklets. Free fall, substitute minus g for a in all the above equation. So y minus g, we choose upward as a positive reference. And acceleration due to gravity is always downward. So acceleration equals to minus g. Displacement formula, velocity formula, timeless. Start from rest. How far will Pinky and Brain go in 30 seconds if their acceleration is 20 meters per second? We know acceleration equals to 20 meters per second, given. Time taken is 30 seconds, given. Initial velocity is 0 meter per second, implicit. What we want the displacement. Formula. T is known, Jobs a timeless equation. Since final velocity is not wanted, Jobs a velocity equation. And the solution equals to displacement formula. Initial velocity is 0, time taken is 30, plus 1/2, acceleration is 20, time is 30, and squared, we get 9,000 meters. How fast will Pinky and Brain be going at this instant? Acceleration is 20 meters per second, given. Time is 30 seconds, given. Initial velocity is 0 meter per second, implicit. We want the final velocity. 3 formula. T is known, Jobs a timeless equation. Since V is wanted, Jobs a displacement equation. Initial velocity 0 plus acceleration is 20, time is 30. So final velocity is 600 meters per second. How fast will Pinky and Brain be going when they have traveled a total of 18,000 meters? Known, acceleration is 20 meters per second, given. Displacement is 18,000 meters, given. Initial velocity is 0 meter per second, implicit. We want the final velocity. Formula. Since T is not known, Jobs are 2 equations which have time in them. Timeless formula. Initial velocity is 0, plus 2 times acceleration 20, and the displacement is 18,000. So final velocity is 849 meters per second. A ball is dropped off the Empire State Building. The height is 381 meters tall. How fast is it going when it hits ground? Acceleration equals to 9.81 meters per second as the object is free falling. Implicit. Displacement is 381 meters. We choose downward as a positive reference, so a value is also positive. Given. Initial velocity is 0 meters per second, implicit. What we want is a final velocity. 3 formula. Since T is not known, Jobs are 2 equations which have time in them. Final velocity squared equals to initial velocity 0 squared plus 2 times acceleration due to gravity 9.81, displacement 381. And final velocity is 87 meters per second. The ball is dropped off the Empire State Building, 381 meters tall. How long does it take to reach the ground? Acceleration is acceleration due to gravity, as we choose downward as a positive reference. So A equals to G. Displacement is 381. It's a positive as downward is a positive. Initial velocity 0, implicit. We want to find the time taken. Since T is desired and we have the displacement, choose the last 2 equations. Initial velocity 0 times T plus 1/2. Acceleration is 9.81 times T squared. We find T equals to 8.81 seconds. A cheerleader is thrown up with an initial speed of 7 meters per second. How high does she go? And we choose downward as a positive reference. So acceleration is acceleration due to gravity. G, which is downward direction. And that's 9.81 meters per second. Implicit. Initial velocity is minus 7 meters per second because a cheerleader is thrown up against our positive reference, which is downward direction. We want displacement. Formula. Since t is not known, jobs are two equations which have time in them. At the highest point, the cheerleader reverse direction. So final velocity becomes 0. Initial velocity is minus 7 plus 2 times the acceleration due to gravity, 9.81, times the displacement. And the displacement is 2.5 meters, quite high. The ball is thrown upward at 50 meters per second from the top of the 300-meter Millau Viaduct, the highest bridge in the world. How fast does it hit ground? Known. Acceleration due to gravity as a free fall, and we choose downward as a positive direction, and acceleration due to gravity is always downward, so it's positive. Implicit. The initial velocity is minus 50 meters per second because the ball is thrown upward direction, and we choose downward as a positive reference. Given, we want the final velocity here, just before hitting the floor. Since the t is not known, jobs are two equations which have time in them. Solution. Final velocity squared equals to initial velocity squared minus 50 squared plus 2 times acceleration due to gravity, 9.81, times the displacement, 300. And we get 91.5 meters per second. How long is it in flight? We choose downward as a positive reference, so acceleration due to gravity is positive, 9.81. That's implicit. Initial velocity is minus 50 meters per second as the ball is thrown upward at 50 meters per second. We choose downward as a positive reference. Therefore, it's minus. Given. Final velocity, 91.5 meters per second. We have calculated this in previous slide. Formulas. Use the simplest t equation. Final velocity, 91.5 equals to initial velocity minus 50 plus acceleration due to gravity, 9.81 times t. T equals to 14.4 seconds. The slope of a displacement time graph is a velocity. The slope of velocity time graph is acceleration. Suppose Freddy's fly begin at x equals to 0 meter and travel at a constant velocity for 6 seconds as shown. Find the 2 points, sketch a displacement versus time graph, then find and interpret the slope and the area of your graph. When t equals to 0, displacement 0. When t equals to 6 seconds, displacement is 18. The 2 points are this fit line. Rise equals to 18. Run equals to 6. The slope is rise over run, which is 18 over 6. The slope is 3 meters per second, which is interpreted as a Freddy's velocity. So gradient of the displacement time graph gives us velocity. The area under the velocity time graph is a displacement, and area under an acceleration time graph is a change in velocity. Calculate and interpret the area under the given velocity versus time graph. Find and interpret the slope. The area of the triangle is A equals to 1 over 2 times the base times height, which is equals to 1 over 2. Base is 20 seconds and height is 30 meters per second. That gives us 300 meters. This is the displacement of the object in 20 seconds. So area under the velocity time graph gives us a displacement. Slope is 30 over 20, which is 1.5 meters per second. This is acceleration of the object. So conclusion is area under the velocity time graph is displacement and the gradient is the acceleration of the object. Suppose a blue whale suddenly materializes high above the ground. Drag force D is proportional to speed squared. As a whale picks up speed, drag force increases. Once the drag force equals the whale's weight, the whale will stop accelerating. It has reached terminal speed. So at first, the velocity equals to 0, and only force acting in is a weight. Drag force D is proportional to the speed squared. As the speed increases, drag force increases too. Once the drag force equals to the weight, the net force equals to 0, and acceleration is equal to 0, and object reach terminal speed. Suppose you are a passenger in a car on a perfectly level and straight road, moving at a constant velocity. Your velocity relative to the pavement might be 60 miles per hour. Your velocity relative to the driver of your car is 0, whereas your velocity relative to an oncoming car might be 120 miles per hour. Your velocity can be measured relative to any reference frame. Consider two cars A and B shown below. Suppose you are in a car A, which is moving at velocity 20 meters per second, and next to you is car B moving at 40 meters per second. As far as you are concerned, your velocity VAB relative to car B is minus 20 meters per second because you seems to be moving backward relative to B's coordinate system. We write VAB equals to VA minus VB with the velocity of the A relative to B. The equation works even in 2 dimensions. Suppose you are in a car A, which is moving at VA equals to 40 meters per second, and approaching you are right-angled is a car B moving at VB equals to minus 20 meters per second as shown. Since A and B are moving perpendicular to one another, use a vector diagram to find VAB. Draw in the vector and use VAB equals to VA minus VB. VA, VB. We can actually reverse the vector quantity, reversing the direction of the vector quantity in a parallel position. So that's going to be minus VB. Ending of the first vector is the beginning of the second vector. And that gives us VAB equals to VA minus VB. And use Pythagorean theorem, VAB squared equals to VA squared plus VB squared. And VAB squared equals to 40 squared plus 20 squared. VAB equals to 45 meters per second.